Welcome back. In this video, we're going to discuss how the FMA method applies to a system of particles. We've been looking at how FMA applies to a single particle, acting on the sum of the forces equals the mass times acceleration. And it's going to also, of course, be true for, if it's true for one, it's going to be true for the group of them. So if we're going to be looking at situations where we've got multiple particles in space, they can have relationships to each other, they can have some constraints and act on each other, as well as they need to have some external forces acting on them for us to use the FMA method. And then you can probably predict it's basically going to be take all the forces, add them together, and it's going to be the sum of those is going to be the mass times acceleration. So we're just going to take some interpretations of those things and look at them in detail. So let's take a step back and think about what if we were just talking about one particle? So if we have just one particle. Let's take this first particle, for example. It's got an external force F and some internal force where F is acting on 1, this little f is 1 is acting on 2, and 2, of course, is by Newton's third law acting on 1. So they're equal and opposite reactions to each other. So for one particle, we could take the external forces acting on that ith particle, that one particle, and add to that the sum of all of the forces between the particles. So that is all the ij's for all of the internal particles. So particle 1 feels some internal force from 2 and 3 and 4, all the way down however many particles we have. And so the FMA method would say all of those external forces plus all of those internal forces would have to be equal to the mass times acceleration. So the mass of that particle and the acceleration of that little particle. Now we can also, so that's dealing it with one little particle at a time. We can also then look at what if we dealt with the whole system of particles all together at the same time. So for a system of particles, we can think of Newton's third law, and remember that for every action, equal and opposite reaction, or a collinear reaction in the opposite direction. So that means that if you take the sum of all of the little forces, and 1 acting on 2 has to be equal and opposite to 2 acting on 1, so you add those two together, and you'd get 0. And the same would happen when you add them for all of them. So if you sum all of the little internal actions, all of the forces together, those have to be 0. And that's the implication when we look at the system of particles of Newton's third law. So it's important to think about, or to make the comment of what we're talking about. For one particular particle, the internal forces it feels from other particles is very important. It moves around and it accelerates proportionally to both the external forces and the internal forces. However, when we look at the whole system of particles, the whole system of particles has no movement because from these internal forces, because all of them will sum to 0. So instead, what we're left with is that the sum of all of the external forces, and we'll go ahead and recognize that those are vectors, has to be equal to the total mass of the system and the acceleration of that system of particles. And it's true throughout, but most often we care about one particular point. So we might care about how the system of particles is moving with respect to an origin that's of interest to us. Or we might be interested to know how the system of particles are moving with respect to a point that is important to that system, which is the center of mass. So that's what I've kind of indicated here. If we've got 3 different particles, and based on their masses and how they're distributed, the center of mass is a particle, a fake particle, with the mass of all 3 of those in the location that sort of averages out their weights. So one of the positions that we care about is this center of mass. So an important position for us. We want to call it the center of mass. And all the things that are true about the system of particles are true about the system of particles all over the place. So the sum of the forces external is mass times acceleration at the origin, as well as at the center of mass. And so that's where we get kind of the interesting things. So the sum of the external forces acting on our particle, all of the particles, is equal to the mass, which I'll say g, that is the mass of all of the particles together, and the acceleration g as a vector, where we mean the acceleration of this center of mass. I could have also done it at the origin. So how the origin, if we've got a moving, rotating origin, is accelerating, but most often we care about how that center of mass appears to be moving with respect to time. So that's one important aspect, and that's the direct application of our FMA method, force equals mass times acceleration. We also have another principle that helps us settle these system of particles, which is called the principle of moments. So you may recall POM, or the principle of moments. And the principle of moments has a couple different implications, but basically the sum of the moments in the system is going to be all of the little contributions of moments. So the sum of the moments, so if we take the sum of all of the little bits of mass and their distance away from some point, again, we could do it from the origin, or we could do it from the center of mass, are equal to the total moments on the system itself. So we could say the total mass of our system and the position of that center of mass with respect to something we care about, such as the origin. So if you measure r here with respect to origin, this would be also the center of mass distance with respect to that same origin. Now we can take derivatives of this, and then we get the other implication of the principle of moments is that the momentum, the mass times velocity of all the little bits of our system has to be equal to the momentum of the whole system. So it's fairly intuitive when you describe it that way. If you got a little momentum here and a little momentum here and all over the place, and you add up all of those little bits of momentum, of course you're going to get the momentum of the whole system. But mathematically, that looks like the sum of all of the momentums from all the little particles, momentum being mass times its velocity, is equal to the mass, the center of mass, total mass, times its velocity. And of course, you can treat those both from a vector perspective. So these are the two principles that allow us to approach systems of particles. It's just the one extra that adds the detail to how we solve these. Of course, we've got our FMA method, which is that the sum of all the external forces on the system change how the total mass of the system is going to move. And then we generally look at the center of gravity, how the center of gravity is accelerating or changing its position. Further, we can apply the principle of moments to understand how all of the bits, the moments caused by those bits of particles on the system, how they're going to affect the total moment of the center of mass, and how all the little bits of momentum, that is their mass times velocity, add up together to be equal to the total mass, total momentum of the system of particles.